Okay, so now we are done with um, what stress tensors are, what strain is, the relationship between them for the materials that we're dealing with in this class, and how to transform stress tensors into different coordinate systems. Here's a question. If you were given a strain and you wanted to represent that strain in a different coordinate system, how would you do that? You can't do that because the strain is only in the Voigt form. And really, so you might think like, well, put it in a matrix like the stress. You know, we haven't done that. The reason we haven't done it is because strain is not a tensor. And that tensor, the thing that tensors have that other matrices, 3x3 matrices, don't have, is that you can re-express them in another coordinate system using rotation matrices. So you can't do that to the strain. If you define the strain differently, you can, but we're not doing that. So exactly, that's the only way you can do it. So it's a total pain in the butt, but that's how you have to do it. So if you want to go, if you have the Voigt strain in one coordinate system, and you want the Voigt strain in another coordinate system, you use the first coordinate system to figure out the stress, represent the stress as a tensor, do the stress rotation, the coordinate system transformation to go to the new coordinate system, and then use the stiffness compliance matrix again to recalculate the strain. Okay, so the only, like I say this in dynamics sometimes, like the acceleration is the skyway between kinematics and kinetics, you know? Like no matter where you are in kinematics, if you want to get to kinetics, you have to first go to acceleration to go across, you know? And it's the same thing with stress and strain. Stress is the skyway from one coordinate system to another, you know? No matter, you have this strain stuff, first you got to get to the stress, go across, and then you can mess with it. Okay. What? Yes. So what if we had the Voigt strain one coordinate system and wanted it in another coordinate system. Strain isn't a tensor. And so the way that you have to do it is first you'd say the Voigt stress is equal to the stiffness matrix times the Voigt strain. Then you'd represent that Voigt stress as a stress tensor, and the stress tensor in the new coordinates. Sorry, let me put another step in here. And so let's say that that. Okay, let me do it like this. Okay, so that's the Voigt stress and Voigt strain in the old coordinate system. Then the stress tensor in the old coordinate system get that from the Voigt stress in the old coordinate system. Then the stress tensor in the new coordinate system is equal to Q stress tensor in the old coordinate system times Q transpose. And then the Voigt stress in the new coordinate system you get from that tensor. And then the Voigt strain in the new coordinate system is the compliance matrix times the Voigt stress in the new coordinate system. Maybe I didn't need to write it in that many steps, but I have those 2 steps just reminding you that for some of that stuff it needs to be tensors, for some of it needs to be Voigt form. Okay. I don't think there's any questions I ask in this class where you're given a strain and you have to transform it, but that's what you would have to do if you were in that situation. Any other questions about that? Number 1, that's the stiffness matrix. So that's just saying, the stiffness matrix is the inverse of the compliance matrix. Yes. Yep. If you just like put your matrix in well, you don't even have to put it in a variable. It can be in a variable or just a matrix, and then just go power of -1, and it does the inverse for you. Yeah, the TI calculators are really good with vector and matrix calculations, and I feel like people, like a lot of times, people, don't know all that stuff's there. It does all this stuff that would be a super pain to do by hand. Any other questions about that? I don't even know why I talked about this, but this was all part of saying that we're done with the relationship between stress and strain, switching coordinate systems between stress and strain, principal stresses. Okay, question? Oh, scroll. Mm-hmm. Okay, yeah, no, I haven't. Okay, so now basically for the rest of the class, I feel like I'm teaching in a movie all of a sudden. Like I'm about to have like a really important realization. Like every student has something to offer. So the rest of the class will all deal with calculating stresses based on big objects with loads on them. So going from external loads on objects to stresses at individual points. And, all of these stress calculations are going to be based on assumptions. And so we're going to do it for, well, what if you have beams with this, and we'll learn some things. How do you calculate the shear stresses from this kind of loading? And it's just going to be sort of a catalog of these things sort of the rest of the semester for the most part. All of this is going to be based on one really important called St. Venant's principle. So all of this will depend heavily on St. Venant's principle. St. Venant is a person. This is the other kind of principle than not like principal stress. This is like an idea principle. And St. Venant's principle basically says um, for any loads you can replace the occurring loads, the actual loads, with uniformly distributed loads as long as um, you ignore points near the loaded face. Okay, so let me give sort of an illustration of this. This idea is pretty simple. It sounds sort of wordy the way I said it there, but um, so let's say that you have an object like this, okay, and you're applying point forces here and here. Okay. Well, we don't have a way to do that calculation, but we do have a way to, the first thing we'll talk about is how to do a calculation like this. So if this is F and this is F, this is F and this is F, okay? As long as we throw away any information we get about this, we just don't want to trust stuff here close to those loaded faces. All the information, so say that this is how the beam is really loaded, okay? We don't have a way to do that calculation, but we have a way to do the calculation of the stresses and the points in this one, okay? So what we're going to say is, we're not going to trust anything we get from the two ends. Those are the loaded faces. And everything in here is going to basically be correct, okay? And why don't we want to use the points close to the loaded faces? Well, if you think about what would happen in these different cases, this is a pretty exaggerated deformation, but so if you're applying these forces at single points, you're going to get this weird deformation here where that single point is stretched out more than the other points. And since deformation and, since stress and strain are related to each other by this matrix, if the strains are super different between these, then the stresses are also super different between those, okay? And so all the stuff going on close to that point is going to be garbage. What your calculation is going to be garbage. All right, well, is there ever a time that what you really want to know about is what's happening at those 2 points? Yes, there definitely are times where it's an incomplete picture of what you want to calculate all the stuff in here. But there are other times that it's really useful, okay? And the examples that we're going to do in this class are the ones where you get really useful information from what's happening in the middles. Okay. Um, so from this and this, the idea is uh, the behavior near the loaded face is very different. Okay. So what's the next question that comes up is, well, how near is too near? Um, and that's really, it just depends on largely on how much precision you want. But I can give you sort of a general guideline that people use. So how near is too near? And the answer that people use is within about the length dimension of the loaded face. Okay, so you can see that's about what I drew in my picture. The length dimension of this face is like this. So that's how far I allowed to move away. And then once I got this far away from the end, then I trusted the values. Um, that means that if you have an object like this and you're applying forces to it like this, we can't get good values anywhere. There's really nothing we can say about this. The profile of stresses is too complicated. So it means in a shape like the one I drew below, you can't trust the stress values anywhere. Unless you happen to have a distributed load that, unless the loading exactly mirrors what our calculations are based on. You know what I mean? So if, like, for example, if we had uniformly distributed loads on those two sides, then that's exactly what our math is based on. So then we get good values. But point forces like this, we wouldn't be able to do it. So how would you do it if you're working for a company and you had to figure out something like that, or if you had to figure out what was going on in those regions that we want to be careful about? You do it with finite elements, with finite element analysis, computer, expensive software packages. And so what we're doing, practically speaking, is we're getting kind of sanity check results that you can compare to your finite elements calculations in some cases. And then largely what else we're doing is just starting to wrap our heads around what stress and strain are and how they relate to each other. But like Medtronic doesn't have anybody doing, presenting hand calculations of stress and strain. They have people who are good at hand calculations of stress and strain using finite elements and then using their sort of background knowledge to convince themselves that these results make sense or don't make sense. Okay, so every kind of stress calculation we're going to do is going to depend on St. Venant's principle. And the first category that we're going to deal with is, I don't know, I'm going to rename this sometime. If you fail this class, it might be renamed when you take it next time. So right now it's called objects loaded like big stress tensors. Sorry, big, like big stress elements, big stress cubes. And really, mainly, this is just tension and compression. Um, okay, so if you have um, an object that has forces applied like this, and this cross-sectional area is A, and let's say that we have a coordinate system like this with the x-axis along the loaded axis, y-axis, z-axis. Then the normal stress is equal to F over A. So for example, let's say you have this circular cylinder and it's loaded with 5,000 newtons of force that way on one face, and 5,000 newtons of force this way on the other face. And let's say that the length is 0.1 meters. And the radius of the face is 1 centimeter, 0.01 meters. What's the stress tensor at points inside the body? And where do we trust those calculations? Okay, well, I'm going to use a coordinate system with the x-axis along the loaded axis. And the stress in the x direction, the normal stress in the x direction, is, okay, so look at the directions of those. So on the positive x and negative x faces, we have loads in the x and negative x direction. Are those loads positive or negative? Those are negative, so we have negative 5,000 divided by the cross-sectional area, which is pi times 0.01 squared. And we get a value of 1.59 times 10 to the 7, negative 1.59 times 10 to the 7 pascals. And so the stress tensor is negative 1.59 times 10 to the 7, 0, 0, zeros. This is pascals. Oh, one thing that I saw a lot in the binders, really the only thing that I saw regularly that I'd like you to correct is not putting units on your answers. So be sure all your answers have units. Instead of oh, oh yeah, sure, yep. But draw a bigger cube too. Okay. Yes. Hmm. Oh yeah. Well, think of it as like if this is a stress. So this is kind of like why I have the kind of cumbersome name on this section. Like imagine this cube where this is the x direction, y direction, and z direction. Okay. And what we have here is on the positive x face, we have a 5,000 Newton force going in the negative x direction. So we have our 5,000 divided by the area going that way on the positive x face and this way on the negative x face. So if you think about the way it works on a stress cube, that always tells you the signs. If we were just talking about normal stresses, tension is always positive and compression is always negative. So in this case, it's in compression, so it's negative. But you can also just think about, so imagine reshaping this thing into a stress cube, and then the direction of those forces tell you that it's a negative normal stress. Tension is positive. Yeah. And if you remember from statics, that's how it went in statics too. So the when you calculate like tension or compression values in a beam or in whatever, you can just use the signs of those values you calculated using the methods of statics. Okay, so we get this stress tensor given the coordinate system that I gave you. And now if you wanted to get the strain, you could use the compliance matrix and calculate the strain and whatever. So tell me now so based on this, uh, what would you get non-zero values for the strain? Except what? So you would get, so if you have a negative value of this stress, okay, you'd also have a negative value of the x strain, normal strain. You'd have positive values of the normal strain in the y and z directions because of the Poisson's effect. When you crunch it down, it squishes out. Okay. And then you'd have no changes in angles. You'd have no shear strains because there are no shear stresses. So you'd get three non-zero values, and they'd be the normal values of the strain. One kind of problem that we're going to do a bunch of. This is the main place in this class that we're going to use statics. So kind of structure has tension and compression only. In every member. Truss. Okay, so let's do an example of a truss problem, because I think in the homework there's a few of those. So let's say we have I just got so excited. Okay, so let's do a simple truss problem. Where this is an equilateral triangle. And let's say the lengths of every member is 1 meter. And the load we're going to apply is like this. So 1,000 Newton load. And let's say each one of these members has cross-sectional area of, let's say, 1 times 10 to the minus 4 meters squared. And so I'm going to name these, I'll call this member 1, member 2, and member 3. What are the stress tensors of the members? Of points inside each member. Okay, so the first thing we have to do is calculate the tension or compression in each one of those members. And a little bit of a pain, but people who took statics from me, we tended to calculate it one way, and the people who took statics from anyone else calculated it a different way. So I'm going to go through both of the two ways. You can sort of see how it works. And, so there's two ways to do this. Sort of a general approach. That's the way that we always did problems like this in my statics class, and it works for any kind of problem. And then the truss simplification that saves you some equations, saves you some time, but it only applies to trusses. Okay. So first, I guess let's do the general approach. Okay, so for this, I'm going to treat each of those bodies as a rigid body and go through Newton's laws with each one individually. Um, so uh, we're going to isolate each member as a rigid body. Um, and so free body diagram of member one. Uh, so, and we, is this going to come up in this? I suppose it is. So we have to decide, unless we're going to treat the individual pins as their own bodies, we have to decide which member we want to associate the pin with. Okay, so the way I do it is, you can do it any way you want. You just have to be organized about it. But I always say the pin is part of the lowest numbered member that it touches. So, point. So if I name these joints, let's call this A, B, and C. And if you look at them from the side, um, you can think of it as like uh, there's the ground, and there's member two, and there's member one, and the pin is part of member one. This is just kind of a way to think about it. It's not, that would not be a very stable way to make that joint, but so think of the pin as being part of member one, not part of member two, and not part of the ground. Okay. And so down here at joint A, what are the forces applied to member one? Yep. And so I'm gonna write it as there's a force um, on one by two, and then there's also a force on one by the ground that, I'll call that the reaction force. Okay, this is joint A. And now at the other side, at joint B, one is the lowest numbered member of that joint, so we're going to assume that that pin at B is part of member one. So again, we have member one connected to the pin. And then we have member three not connected to the pin. And then we have that 1,000 Newton force applied to the pin. So here's member one, here's member three. So up here at joint B, what loads are applied to member one? Yeah, F13. And the 1,002 because that's applied to the pin. So um, And now we can, I'm going to write out row vector, the force vector, and the moment vector. We're going to use Newton's laws for this. So I'll choose the about point here, I guess. So first, the force F13. What's the row vector for the force F13? If the red dot's the about point, the row vector goes from the about point to where the force is applied. That's 0. The force vector is F13x, F13y, and then cross product is 0. Then the 1,000 Newton force, that also has a row vector of 0. The force vector is 1,000, 0. Cross product is 0. And then the force F12, what's the row vector for that? Well, this angle is 60 degrees, so it's going to be, and the length is 1, so this row vector is going to be negative 0.5, negative 0.866. The force vector is F12x, F12y. Cross product is negative 0.5 F12y plus 0.866 F12x. And then the last one is the R vector. The reaction force R. That is the same row vector as F12. The force is Rx, Ry. The cross product is negative 0.5 Ry plus 0.866 Rx. And now Newton's second law, we can just add up these forces and set them equal to 0. So F13x, F13y plus 1,000, 0 plus F12x, F12y plus Rx, Ry is equal to 0s. And the moment equation, rotational Newton's second law, says, we're just adding up everything in the last column. Says, I'm going to rearrange these a little bit. 0.866 F12x minus 0.5 F12y plus 0.866 Rx minus 0.5 Ry is equal to 0. Okay, can we solve this yet? No, because we have 1, 2, 3, 4, 5, 6 variables and 3 equations. We're going to have to isolate something else. So I'm going to do the same thing now with body 2. So at the left is joint A, and at the right is joint C. So let's draw what's happening at joint C. Um, yeah, yeah. And this doing a problem like this way makes me a little self-conscious because this is the worst this approach can look. This is a problem that's cooked up to be easy for a truss simplification, and so there's a lot more equations and a lot more pain to do it in this general approach. But uh, how like think about this. What if we wanted to do a similar problem to this, uh, but we wanted to like notice right now we're not including any weights. So right now the truss simplification works great. Okay, let's add the weights in here. You can't use the truss simplification anymore. Well, that's a sort of a big weakness. Or what if this force, you moved it down from the pin down to let's figure out what it would be if that force was applied here or something. Can't use the truss simplification. So if you have a perfectly cooked up problem, the truss simplification is so quick, you know. For any other problem, this way of doing it will give you, you can use it with no restrictions, you know. So that's the benefit of it. But you can do it however you want. I'm going to just do a refresher of both of these two methods. Question? Okay. Okay, so over here at joint A, so let's look at this sort of sideways side view of joint A. Uh, what forces are applied to member 2? What's touching member 2? Only one. So over here, there's force on 2 by 1, and that's all. And then on the other side, I'll do a side view at joint C. So what's, okay, so we have, for the joint C, we have member 2, and that's the lowest numbered member at this pin, so the pin is part of that. And then we have member 3, and then we have the roller that's in contact with the ground. Okay, so this is member 2, this is member 3, and this is the roller. So over here, we have the force on 2 by 3. And then we have the upward force applied to the roller that I'll call FR. And I guess I'll choose the about point over here. Okay, so Newton's second law, I'm not going to write out rho and force and moment on this one. It's a little simpler. So Newton's second law says F21x. Oh, and before I do that, we already have an F12, so let's use Newton's third law. Okay, so negative F12x, negative F12y. plus F23 x F23 y plus 0 FR is equal to zeros. And then the moment equation, we have no moment produced by FR or F23. The only moment is counterclockwise moment produced by the negative F12y. And it has a moment arm of 1. So that's a positive 1 F12y is equal to, oh, let's see, F12y. If F12y is positive, yeah, right. Okay, can we solve this yet? Now we have 6 equations, but we got 2 more variables, so 3 more variables. So now we have 9 variables, 6 equations. So we're going to have to isolate the last body too. I'll do that next time. Yep. Yeah, that's what we're doing. I think what you're talking about, I'll do that next time after I finish this one. There's sort of 2 ways to go about this. And so we'll get the same thing both ways. All right, that's all.